Michael Phillips from Lockheed Martin, and I'll be presenting some of the results from a R&D effort we did in 2013, and Amy Mock was my technical lead on this, and we'll give you an idea what we are doing to discover design patterns in existing flight software baselines through Lockheed. In order to get the IRAD funded last year, as most of you know who work some R&D programs, you're competing against other company efforts and looking for funding in that. So I had to develop a business case at the end of 2012 to look at studying this. So I'll give you an overview of that business case and introduce you to the project, and then Amy will walk you through the selection of some of the COTS tools that we use to run this R&D effort, a little bit about the processes we developed to actually go and discover those design patterns, and then some of the technical tasks, what domains we focused on and what we did, and then some of the results and the observations from some of that. Just a little background on Lockheed Martin and my role in that. So I sit at the software engineering enterprise level across all the programs within the company. We typically develop spacecraft flight software in 3 different physical locations. We have a Northern California Sunnyvale plant. We have a Denver, so that's kind of Heritage Lockheed, Heritage Martin Marietta in Denver. Then we have commercial and military stuff going on in our commercial division, typically outside of Philadelphia. So 3 different physical locations. We have NASA interplanetary missions. We have Earth orbiting missions, military customers, national space, and commercial. So even within some of those campuses, we have programs and people and buildings really that have never left those particular programs and those customer bases. So we had a suspicion that we could actually discover a lot of commonality in design patterns of some of that flight software functionality in domain areas through that. And that's what we based some of this study on. So the business case, you'll see a couple charts up there, but went back and looked at probably 5 to 8 programs that we had been executing on. The program A there you'll see is still in it's between CDR and flight, but most of the programs had already launched, and I looked for historical data on reuse from the proposal phase, PDR, CDR. In some cases there was, as they started coding, they had to do a current best estimate, and then when we actually qualified the software. And I looked at these trends in reuse, modified, and new, just to kind of explain the terminology that we use. Reuse typically is 100% code module untouched. Modified is obviously some modification, but we don't draw a clear distinction between modified and new. What I have seen on most of our programs is somewhere between 20 and 25% modifications to a particular code unit hits the threshold of calling it new. So some new code that we call in this category could be 30% mod, or it could be 100% new. And I didn't have that granularity with some of the data. For some programs, I had data much lower than this level. So this level is kind of a roll-up of a CSCI. You'll see the flight software executable on a couple of those, and in the upper right corner is bootstrap code, which shows similar trends. But behind this, I had information on domains, so we typically break this down into 8 to 15 domains, GNC, power, thermal, executive, and stuff like that. So I had history behind that of what showed the most growth. And then on some programs, I even had it down to a file level. Like in that domain, there was a certain set of files. Some files were reused and some were modified where it was. So I can kind of look at some of the trends and why these existed. So a couple observations here. One is that if you look at the red line, which is new, which you can equate to, all right, more effort to do that, right? It might, that behind that new code might be new functionality, new implementation, new design. So I'm going to probably spend more time writing and testing that code compared to reuse. Just was in general seeing this trend from what we proposed to what we actually ended up with at the end of the program. And then saw this basically deterioration of things that started as reuse, probably moving into modifications, then moving into new. You know, could be because of discovery of new requirements or changes in the program baseline that were not necessarily estimated in the beginning. Wasn't really focused on why we were seeing those changes, just the fact that they were happening, and how could we provide programs with information on the designs that they might eventually have to do significant modifications for a new functionality or develop a new capability. And if that capability had already been designed by a different program in a different building or a different location, how could we help the productivity of either the individual software engineers or the team? And what I mean by that is, if you look at the composition of our flight software teams, 10 to 20 people. Sometimes you get new people, college graduates or new people to the area. Maybe they have done embedded software but not in spacecraft. We also have people on teams that have been doing a certain set of domain software for several programs, and they're ready to move to a different domain, so they may not necessarily have knowledge in that area, and giving them heritage software designs would help them in their effort. And then there's really the top-down approach of the team effort, meaning if you know you're going to see this trend, how could you, from the top-down manager and technical lead, make sure that when that need arises for a new design, right, that those designs are already there on the table and able for them to reference. So some hypothesis there was that the new software that we're developing is similar to things we've done before. In some cases, it is actually brand new, but it even takes something as you're flying a new set of instruments or new payloads, that general capability to do payload management and control is something that we've seen before and we can discover from different programs. In a lot of cases, it's platform upgrades due to bus components and new communication systems, a new GNC system and stuff like that. Maybe that program hasn't experienced that change before, but we can provide those reference designs. Our hope was also that a lot of that heavy modifications of code was preceded by a design activity. Obviously, some of those mods could be modifications to just the implementation that don't require design, but our assumption was that new code required a set of requirements and basically a full life cycle so that we could help them at there. And then we also found that we are historically spending a lot less time in the code phase. So we spend time doing requirements, design, right? Not a lot of time, and we're good at writing code, so we really focus on this design phase and trying to improve productivity. The bottom there is really saying, all right, if we now found, if we go through this process and we find multiple designs, in order to provide a reference design to a program, we'd have to go through a selection process of compare those designs to others and provide some reference information so to help that program select the best design. Just a quick overview of the project itself. So if we look at the definition of there as to what we did, this was first a discovery process. So we're hoping to find COTS software products that allowed us to essentially reverse engineer the code and objectively discover designs, right, that we could compare between programs. We were doing it on TRL-9 flight software, meaning already operational code that was already running. And then our goal was to actually take the best practice design, right, and create these reference designs in certain domain areas to prove that it could be done. It was split into 3 tasks. One thing unique about the IRAD this year was for this particular program and a couple others, they gated our IRAD, meaning they gave us it was a full year program where there's a set of money, but they said about halfway through there, you need to get through task 1 and part of task 2 and show that this R&D has value, right, and it's actually going to work. The COTS tools are doing what you thought they could do, and you can actually discover patterns and put them on the shelf, and then they release the additional funding. And that was actually a good motivator for the team to be focused on, all right, we don't have a whole year of funding, we actually have to get through some milestone reviews and prove that there was value, and we also had to line up some customers within our company that were going to evaluate some of our processes and artifacts in the end. Next slide. Oh, sorry. So a couple things we were, design patterns means a lot of things. We basically just simplified it into 4 different areas: architectural patterns, functional, logic and algorithm, and implementation. In this effort, we really were not focused on looking at architectural and implementation patterns. So a little about architecture. You can use tools to discover flight software architectures, right, how domains go together and how they couple. We were really looking at functional capabilities within a domain. So you could say that was a component architecture or a functional architecture down there. So we did discover some things in commonality with, the way we sent commands and provided state of health telemetry, how we initialized the unit, and you could consider them architectural types of patterns, but really at a lower component level. In the implementation patterns, a lot of documentation and books out there on design patterns for C++. We also weren't looking at those. We were really focusing on functional requirements at that functional level, and also algorithms and the logic surrounding them. For instance, a lot of our programs are migrating from historical battery charging to lithium-ion batteries. And as they migrated to lithium-ion batteries, you said, all right, we have a couple programs that have flown that. When other programs go to that, how do we share that knowledge of how they do battery charging from what they've historically done to a new set of hardware? That's it.
I'll just use this. Okay. All right, so there's two use cases for our research here. The first one has it will benefit the specific flight software program immediately. And the second one on the bottom here benefit the enterprise to help future programs in the long run. So if you look at the first swim link on the top there, we help programs to run COTS tools on hearsay code. What we did was we tried to generate reverse engineering diagrams for the programs and help them understand their heritage code easier and faster. At the bottom here is the second swim lane where we help enterprise to find common design. So we first select a few flight software domain area, and then we collected software documentation, design models, and we also collected the code. And for the code portion of it, we do the reverse engineering with the tools that we procured. And from all of these artifacts, we were able to create the modular common design, and we store them into a reference design database, which future program can access. So here's a list of tools that we try to explore more of. So all of these tools said that they will provide more features for us to pattern detect the code. So what we look for in the tools is the reverse engineering capability, metrics collection, and also if they support a specific software language that our code baseline are in. So we did a preliminary trade on each one of them, try to get more information by reading their technical spec, try to get a demo from them, or just get a 30-day trial version. So we wanted to understand if they can really do what we need. Okay, so each tool can provide a wide variety of capability for us, so it was very difficult for us to choose which one will benefit us the most. So what we did was we tried to create a sample code to test out their claimed functionality. So the code that we created was geared toward trying to exercise how well and accurate they can detect the relationship or dependency between classes and show us the flow of the code. And from there, we selected the 4 tools. Those are the ones that we use to run our code baseline on. So reverse engineering, the ability to create reverse engineering diagram was one of the most important capability we look for in the tools, as I mentioned before. This is essential for us because it helps us understand the code we're not really familiar with. And the diagram that you can create include the architectural diagram, which show us the key component of the system and how they're actually laid out. And then the class diagram, which is important for all class, object-oriented software. And it shows us all the classes and the relationship between them. And the function call diagram, which shows us a particular function, who called that particular function and who it actually called. Dependency diagram will help us look at a particular file, who called that file and who it also used. And then the logic diagram, which shows us the flow of the particular functions. So being able to visually look at the code, it makes it much more efficient for us to understand what is inside that software. So metric collection, as I mentioned, is another very important capability we look for in a tool, because we believe that it can actually give us a good quantitative measure of what the code is and understand the quality of the design and to find the best practice for us to create a reference design. So there's a few metrics that we use here. The complexity, which shows us how well structured the code is and how difficult it is to write and to maintain it. Cohesion and coupling, that will show us how well classes are encapsulated and how easy it is to maintain the code. Depth of inheritance will show us how many layers of inheritance there are in classes. And the more there are, that means the code are more complex. And then slots, which is a measurement of the module size, which help also estimate the maintainability of it. Okay, so after we select all the tools and capability, how are we going to go about identifying patterns? So this is the process that we created. So we first gather a bunch of different inputs, which include source codes, software model requirements, and any other documentation from programs so that we can understand the software a little better. And from there, what we did was we chose 3 particular domain areas to focus in, which include the thermal control subsystem, power subsystem, and 1553. And even from that, we also further look at the patterns functionality. We chose the thermostatic control and battery charging for our study in particular. And after we were able to pull out patterns from those functionality, we start evaluating the patterns using metrics, and that will help us understand the quality of the code. We also try to use this trace study tool to help evaluate them. What we did is we create bins using associate metrics, and we try to score each baseline accordingly. But we found that this tool is not really that useful for us. It's only useful if we're really comparing functions that have like the same input and output, very, very similar type of function. But what we found is each code baseline are coded a little differently, so it was very hard for us to use this tool as much as we wanted to. So after the evaluation, we did the implementation of the patterns using modeling tools. So we use some Rhapsody and also integrate that with some Simulink modeling. And the next step for us is actually deploy the patterns into actual program, which we haven't done that yet, but we will do that in the near future. Okay, so one of the reasons the tools are very valuable for us is that it can show us the final design of the software. Being able to use the reverse engineering capability, we can see the truth of what goes into the software. So what you see here is a generalized class diagram that resembles a code baseline that we analyze. So on the left side here is a detailed design diagram that you usually find in a design model. And on the right is actually reverse engineering diagram that was generated from one of our tools. And here you can easily spot some similarity here. You can still see the composition and the inheritance relationship, and also some direct mapping of the classes. But then you can also see some differences. So on the left, the logical architecture domain class is actually split into 2 classes in the actual code. And also the attribute and operations are split as well. And this is the reason why we cannot just rely on the design artifacts alone, because sometimes decisions are made afterward, and somehow it just didn't get flowed back into the design documents. So we have to use the reverse engineering tools to help us see what is the actual software, what is in there. So here's another example, but this one is on the behavioral diagrams. On the left is a generalized sequence diagram that you find in a design model. And on the right is actually the logic flow diagram that was generated from one of our tools. And you can easily see the logic, how they map to each other. Even though like the reverse engineering tool wasn't able to generate the same type of sequence diagram, but with the logic flow diagram, we can still see the similarity from them. So another thing we can do is actually requirement trace. So as we analyze the logic flow of the code piece, we were able to do some requirement traceability. This is very helpful for programs that have very similar requirements with this program showing here. So they can actually analyze what this program has, how they actually implement and design their requirements, and try to do some reuse here. So again here, the tools actually make it much easier for us to visualize the code and show us what the software is like. So after we review the code and all the relevant documentation, what we did was we come up with this first cut of reference design here. So you see some functional and also logic patterns here, as Michael mentioned earlier. Also the color coding here. So each color represents a particular program and what functionality they have. So what you're seeing here is a battery charging example. So in all battery charging, we process sensor input first, and then what we do is we calculate state of charge using a particular algorithm. So you actually see some variety going on here with different programs, and program B kind of look very different from program A and C. And the reason is that the chief battery engineer find a way to simplify the algorithm. He found that it's not really necessary to use the current temperature calculation, as the effect was way too small, so he kind of eliminated that part of the algorithm. And also for the aim-hour integration, he also found that that's not necessary, but that's more of a system design decision that they make. So after that, we will calculate the battery charge rate, and then we'll send the command to charge the battery. And on the far right over there, there's also an option to set manual mode, which allows ground to control which charge rate to use. So you see a lot of commonality in a function. That probably means that functions are critical function that all battery charging should have. But if you're only seeing like a few baseline that has that function, that might mean that is a more program-specific functionality. But then it also may mean that other programs just didn't consider using that function. And this diagram is definitely a diagram we can pass along back to all future programs. So individual contributor from that program can actually understand this domain if they're not familiar with that. And for future programs, they can also consider other best practice that other program has that they didn't thought about before. Okay, so there's quite a few of challenges along the way as we try to create the reference design. The first one, it was actually very difficult for us to obtain the code baseline from different programs. There's a procedure we follow to get approval from programs. We actually have to work with the legal department, draft a letter to the customer, and just wait for the customer to say, yes, we can use the code. And that's really time-consuming and very difficult for us to go through. And then also programs may have different priority. They might be busy with trying to finish their development or testing, so our requests just get pushed on the side until they have time to help us here. So after we obtain this, some of the baseline, the next step is for us to find common design. So the tools are great. It helps us a lot, but there's still a lot of manual effort that we have to do. The tools can help us parse through the code and show us the relationship between classes and the logic flow. For example, the battery charging example I showed you guys earlier, what we noticed is that all the code baseline are coded very differently. So we were able to find the functionality, pull out those battery charging functionality, but we think that's partly because the originated engineer did a really great job of naming the function, so it helps us really focus in that area and say, oh, that is part of the battery charging algorithm. So as we look at each function also, you may see one program, they implement one function with a set of input and outputs, but in a different program, they may implement the function in a number of different functions, use very different input and outputs, and also use very different data structure and store information very differently. So it makes it really hard for us when we do our evaluation. We try to systematically evaluate them, but it was just way difficult because they are so different. So we cannot really objectively pick the best design out of all the code baseline. And sometimes programs also have very different capability. As a result, they are coded differently due to their goals. So there's a lot of filtering that we have to do because of all this program-specific decision that they make to implement their code. So we have to consult with a lot of programs and just understand why they are coding things in a certain way. And this is absolutely necessary before we actually filter out the common design. So also, as we talk to various programs, they're really more interested in finding common design in their own family of heritage programs, and they're not very interested in what other programs are doing. And we think maybe that's because they're just not familiar with other programs, so they don't see how other programs can help them. And on the other hand, on the heritage program, they're more familiar with that, and they can actually already see some commonalities, so they kind of wanted to see the program and how they can help them. So by having us showing them what we did, it actually opened the eyes of the program manager and to see what can be possible and how they can actually leverage best practice design from all spacecraft flight software to achieve more affordable for the company. And with that said, I hand it off to
So
Michael.
in summary, I think we believe there's a good way to improve productivity, right, for those programs. Historically, we're seeing these trends of new functionality, modularity, and if we see it happening on one program and then we know another program is upgrading to that capability, we'll provide that data to them. Like Amy said, the COTS tools are really great about doing a lot of that work. They actually are able to capture the as-built design as opposed to the as-intended to be built design, so that helps us a lot. And they provide a lot of useful insight with the graphical nature of plotting this data, and actually you can interactive with some of the tools, go down and understand what that design is. So there's definitely benefit for individual contributors improving their productivity on a particular team when they are not familiar with that domain or they're considering a new functionality in that domain themselves. And as program teams and leadership, right, if we can provide these set of artifacts, and it's looking more like now that as opposed to a best practice reference design, we'll provide reference design from a variety of programs that they can look at really quickly and get in contact with that program and understand, right, if that's something they're interested in doing, how they want to use that, rather than try to formulate into a best practice design. So providing these that information on the design artifacts to the programs and the individual contributors, we think can help in commonality across all of our product lines and also improve the productivity in the future as we start implementing new functionality. Open it up to questions.
Are there any questions? Thank you.
Well, I commend your effort. I imagine it's kind of daunting to have so many historical programs around there with different vintages of hardware sophistication, software sophistication. Earlier today, the keynote speaker pointed out that they have, by the standards they're operating under now at JPL, that there's an inverse relationship between assertion density and fault density, which is given some really dramatically good results. But historically, when you point out your slide about reuse of code, that code could very well be 15, 20 years old, and these concepts weren't known at the time.
Correct.
Okay. The other thing is you're at a unique level at the enterprise level to look down and see all these stovepipes of development and activity. but who may very well not know much about each other at all. And now that you're finding these things out, do you have any plans how you're going to organize like working groups or something to bring attitude control people together, bring thermal people together?
Yeah, I think we chose simple domains in the first place, battery charge and thermostatic control, which typically are not changed significantly on programs in there. But our intent was to start with something simple and then focused on really guidance, nav, and control and other things. And along the way, our company is moving toward model-based development. So some of the examples that Amy gave, right, we had a bunch of hand code, and we had programs that were in Ada, C, and C++, right? So we looked for tools that could do that. But when we created the best practice reference design for some of those, we moved it to Simulink, right? And then we auto-generated the code, and we looked at that. Again, when you auto-generate that code, you can now run these reverse engineering tools and say, do those reverse engineering tools look like the model base? So part of it is really moving our company from, in certain domains, from hand code things to auto code domains and into model-based tools. So we're seeing that movement into UML Rhapsody and into Simulink for some of that. So I think our step is probably to move to a model-based reference design pattern as opposed to passing around C and C++ code. Because historically what we're finding that there's significant architectural differences between our baselines, meaning that some programs embed fault detection and recovery at the lowest level of their module. Other people have it up here, and to try to understand where the algorithm is versus the architectural design as to how they decided to schedule their tasks to run and pass telemetry and commands in there. Again, given the fact that programs will ultimately probably implement the code very efficiently, I still think there's probably, if we can open their eyes to those designs that are out there, then we'll see that migration into that area.
Yeah, it's a unique combination of technical changes and organizational changes to make them happen.
And again, we didn't set our sights too high into changing everything. It was really looking at the performance of a work team. If you take 10 or 20 people and you go to the flight software manager and say, hey, there's 3 new people on your team and they're tackling domains they didn't tackle before, we can improve the productivity of those 3 people by providing reference designs for them. We don't necessarily need to make it a blanket approach for the entire team to go use these techniques. So we're really focusing on how you as an individual contributor might benefit from learning curve or learning new domains by looking at what others have done out there and not necessarily creating a new design.
Okay. Other questions? Oh.
No.
Okay, that answered one of my questions. So you're not actually looking at this as a prelude for software reuse to transplant from one program to another, but are you looking at it to share the overall brain trust, abstracting the design from one program, or are you actually trying to move it to some commonly used models that you would share between programs, and thus create a...
So I think it brought up a lot of,
product.
as we went through this process, for instance, we started early with the intention that we were going to develop best practice reference designs. What we ended up is finding that programs are really interested. So Larry Ellis back here manages our InSight program that's going to land on Mars, right? So the last vehicle we built was in the late 90s. It landed in, 2005, 6, 7. The original brain trust that did that wasn't around, so that was a mid-90s design, right? So we were able to reverse engineer those and provide better information to that team to benefit from. So we did find that the tools themselves give you a lot of great metrics, right? So it opens your eyes to metric-based things. It definitely, if you're a team that doesn't spend a lot of time doing design, you do PowerPoint design and a little bit of UML, right? Then this can provide a very robust set of documentation, that you could provide to your customer or for O&M in there. So we found there's a lot of, I guess, good unintended consequences of the set of tools in the process we developed that could benefit the company. So we're really thinking how we might use the experience from this R&D, right, in future areas that we might want to go into.
And I just want to add, because the code sometimes is just hard to read them, and what we can provide to Larry was showing the relationship of how things are related in the code. It makes it really easier for them to understand the code that they're not familiar with.
Oh yes, I second that. We once resorted to understand to break down the infrastructure and be able to maintain it.
Yeah, the Understand tool worked great for us. And the tools aren't that expensive from the benefit you get out of it. So.
Other questions? Nope. Nope. Okay, thank you.
Thanks.